Hello. This video is about the gain calculator and the slider bar. The goal is to calculate PID gains, or in this case just proportional and derivative gains, so that the system response is critically damped by just moving a slider bar. What we're going to do is go over the first few equations here pretty quickly because they're a repeat of a previous video. Equation 1 is the controller, proportional gain, derivative gain. We multiply the derivative gain by the S operator, that's the Laplace operator. The second order system is non-integrating. In other words, it's a velocity system instead of a position system. This is the closed loop transfer function, the generic form. And then after we do the substitutions of GC and GA into this equation, we get this. And after we simplify it, then what happens is we get the closed loop transfer function just as a simple fraction of two polynomials. And the goal is to place the poles. And we're going to do this slightly different than what we did in the previous video where we just calculated KD. So this is the actual transfer function. Now what we want to do is have a critically damped transfer function. So this is the characteristic equation for a critically damped transfer function. There are going to be two poles at minus lambda. This will be 0 when S is equal to minus lambda. And there are going to be two poles, and they're going to both be on the negative real axis. There's no imaginary terms. So after we expand this out, we get s squared plus 2s lambda plus lambda squared. Now, to make this equation equal to this equation, what we must do is match the coefficients of each power of s. So we have the 0 power of s, which is 1 plus kp. And then we have lambda squared. So if we have 1 plus kp is equal to lambda squared. Then the first power of s is kd plus 4, and that should be equal to 2 times lambda. So we have kd plus 4 is equal to 2 times lambda, and we can solve for kp and kd. You should be able to do this in your head. Anyway, the solution is, this is the Kp, the symbolic solution for Kp as a function of lambda, and this is the formula, symbolic formula for Kd, derivative gain, as a function of lambda. And lambda is the slider bar. When we move the slider bar up and down, what we are really doing is increasing or decreasing lambda. When we move it up, we're making lambda a bigger number, so actually the pole is going more negative, because if you make this bigger, then the pole location to offset that's going to be more negative. So the problem here is we have the capability of making the gains 0 or negative, and you can see that if lambda is equal to less than 1, then this will be 0. And if lambda is equal to less than 2, then the KD will be equal to 0. So what we got to do is make up another case. We have one case that's going to be for the critically damped. Then the overdamped has two different poles. And if you remember from the previous, two videos ago, when the system is overdamped, you have two poles on the negative real axis, but from the axis where there's a minus 2, then the poles go out in either direction. One goes towards the origin, the other one goes more negative. And we'll see that here again. So this is the solution for when the system is overdamped. And it's pretty similar to the overdamped solution. So, to make this as realistic as possible, I made a slider bar. However, the slider bar, it's just got little tick marks here. You can barely see them. The The slider bar, if I move it along in increments of 1, so I can move the slider bar to 6 radians per second, 5 radians per second, 4 radians per second. And what it's doing is it's changing these gains. And if you remember, when I get down to 2 radians per second, let's see if I can get to 2. At this point, we're at that point where you got 2 poles at -3, which is what you can see here. And then what they do is they, if I make the system more overdamped, the poles will separate. We'll be able to see that in a moment. So I have 2 solutions. If I move my slider bar so that it's less than 2, the lambda is less than 2, then what ends up happening is we could end up with a negative gain for the derivative gain, and that's not acceptable. So the secondary equation for the overdamped takes over. See, I have 2 different cases here. And what will happen is that it'll basically just set the derivative gain to 0. So it ends up being a P-only type controller, just like one of the previous videos. So let's take a look at this. I'm going to make the screen a little bit smaller so that we can see more at once. There's a bunch of calculations in here which are the same as a previous video, so I'm not going to display them again. But what I want to do is I want to show the response as I move this slider bar. So let's see if I can move it. There we go. So we start out with a very slow response, and it's taking, well, first thing, the gain doesn't even get up. It's only, the steady state gain is only 0.66, and it takes a long time, many seconds, to get up to 0.66. Then I can move the gain up, and you can see that the response is faster, and we're getting closer to our set velocity at 1. That's our set point for the velocity. And then if I move this up to 2, this is the critically damped response, the minimum critically damped response. And normally this is where you're limited with a normal system without having extra derivative gains. But the derivative gain now will allow us to increase the lambda, and it's moving the pole location also, so that we have a gain of Kp of 15 and a derivative gain of 4. So what it's allowing us to do is to move both poles to 4, whereas previously we could only move the poles up to -2 or up to 2, and then we couldn't move the poles any farther to the left. Now we can move the poles to, it says lambda is equal to 4, but you got to remember that's actually a -4. And I can move this all the way up to 10. That's just a limitation that I impose on myself here. And you can see that the response is much faster. Normally, with the optimal proportional gain, the rise time is 2.5 seconds, but you can see with the derivative gain, we can get a much faster rise time. Now, the question you should be asking is, why is there overshoot when we're critically damped? And the answer is, there shouldn't be. But there is, and the reason why is because the derivative gain also adds a 0 to the closed loop transfer function, and like I said, zeros add energy. So let's take a look at how what it looks like when we don't have a 0. So I've got another, let's go back. Do a split. Okay, and then let's make this a 150. Now, you can see that I have 2 examples. This is the example with what I was showing you with the slider bar and the 0, and this is the example without the 0. Everything is overdamped, and you can see that even though the closed loop poles are at -10, the response is much different. And this is equivalent of having a P minus D controller. In other words, the derivative gain is only in the feedback path. not in the forward path. And the way that it looks on the equations, let me just move up here to the Bodie plots. Oops. Okay. Now we have both poles at minus 10. One more step up. See, this has both gains in the forward path and the feedback path. And in the Kp minus D situation, you only have the derivative gain in the negative path. And this is similar to our PID and I minus PD. And you can see that there's a difference in the response. If I move this up a little bit more, you can see that this little bump above 0 is caused by 0 dB is caused by the 0. This one doesn't have the bump above, and you can see that at 1 hertz, this is a little bit less than 1, whereas here this goes out to the 3 dB point is out maybe at 2. So what is happening is that the 0 will add gain. It adds phase. You can see this is at minus 90, where this one's at minus 180. The 0 adds gain, adds phase, and it also increases the bandwidth. So let's go down and look at the closed loop poles and zeros. I have both poles set at minus 10. And the only difference is that the example here with the 0 has a 0 at minus, what is it, 6.187. So what ends up happening is, if you want to look at this intuitively, you scan from here at the origin to the left and think of this as frequencies. So you get to the frequency of minus 6.187 hertz, and then what's going to happen is that the gain is going to start increasing the phase. You get phase lead, and then at this point the poles will start subtracting from the phase lead. And since there are 2 poles, you end up getting minus 90 as opposed to having the plus 90. So this adds plus minus, and this adds plus 90. This adds or subtracts 180 degrees of phase lag. In this case, there's no 0, so at high frequencies, the phase lag is 180. That concludes my presentation. Bye.